talk a little bit about the motivation behind a prefix sum, because a lot of the times it's important to understand why we need to use certain algorithms, right? So let's look at this problem statement. So we are given an array. Let's just say our array has 4 numbers in it, right? 1, 2, 3, and 90. And then what we want to do is find the sum of each range sum query, right? So we're given some sort of input. The first line of input says like how many queries we're going to have. So query is just like asking the program like a question, right? And then in this case, we're going to ask the program 3 questions. And each of these questions, what we want to ask is, what is the sum between the range from the left index to the right index? So the first line of input would be the sum from index 0 to index 3, and this will be inclusive. So we go to index 0, which is 1, and then up to index 3 would be 90, right? And then what we want to do is add like all the numbers in between 1 and 90. So in this case, it would be 96 will be what we would output for the first query. For the second query, we're going to be going from the first index, which is this 2, to the last index again, which is the 90. And then the answer for that will be 95. And then the third query will be 2 and 2, right? So this would just be this 3 over here. Okay. So let's sort of write a quick brute force algorithm to solve this problem. So we've already read in the first number, which is q, right? And now we just need to read in each of these queries and then calculate the sum. So I'm going to loop through all the queries first, and then what we want to do is like read in each of these 2 left and right bounds of the queries, right? So I'll say int l is equal to int.extent, and then int r is equal to int.extent. And the way how, if you guys are using Java, how nextInt works is it gets the next number after new lines and spaces, right? So if you get 0 for int.nextInt, right? If there's a space, then you'll know that the next number we need to get is the 3. Right? Okay. So after we have this, what we want to do is get the sum between these indexes, right? So I guess just one way we can do it is we can literally just loop through all those indexes. So j is less than or equal to r. And then what we can do is we can add each value at those indexes, right? So I'm just going from, for example, 0 to 3, and then adding everything inside of it in this sum variable. And then after what I can do, I can just print out our results. Okay. Cool. And this is for one query, right? But we want it for q queries, which we've handled it with this for loop. Okay. Let's give this a test run and see if we get our desired answer. It is giving us, yeah, because this should be less than or equal to, right? I think I typed it there. Let's give it a run again. And 96, 95, 3 is what we want. Okay. So this is all well and good, right? But one sort of flaw about this is that it will actually run sort of slow in certain scenarios, right? So I know we talked about big O last meeting before, but to just sort of remind us, how do we evaluate whether a program is like will run in time, right? So this program does give us the correct answer, but just getting the right answer is a lot of times not good enough in competitive programming. We need to have these programs run in efficient time, right? So to evaluate the whether or not a program will run in time is, we can just sort of see if our program has program with around less than 100 million, so this would be 10 to the power of 8 operations will run in time. Okay, and this is sort of a rough estimate. Okay, so a program with less than 10 to the power of 8 operations will run in time. If it's more than this, then our program will run too slowly, and it will probably not pass all test cases. Okay, so let's sort of analyze for this scenario, how, like, for what inputs would our program be running out of time, right? So let's say that instead of having only 4 numbers, we'll have 100,000 numbers, right? So this will be a much bigger array than what we have right now. And then let's say that like the amount of queries we can have will be also 10 to the power of 5, right? So let's sort of analyze like how many operations we will have using this algorithm. And this will again be a rough estimate. So let's say that we loop around q times outside, right? So that will be around 10 to the 5 operations on the outside. And then in the inner loop, we will have, so what we're doing inside the inner loop is we're potentially like adding like some sort of range inside the array. And I guess in the worst case scenario, if we keep adding from like the 0th index to like the last index, right? That could be that we could be traversing the array, the whole entire array, right? So, and again, the array is like has length 10 to the 5. So for each of these queries, we could be traversing the array around 10 to the 5 amount of times. Okay. So again, the outer loop is 10 to the 5. The inner loop could be around 10 to the 5 operations. So we would have a total of 10 to the 10 operations, which is bigger than 10 to the 8, right? So that is like kind of too slow, right? So this is where prefix sums come in. Prefix sums will basically be able to optimize some part of this algorithm to make it run faster. So let's look at which part would we be able to optimize. The first part, 10 to the 5 queries, we can't really optimize that much, right? We will still need to be printing out 10 to the 5 amount of times, so this part will stay the same. But the second part of summing everything inside of the array, we can actually optimize it. So, so I'll say this is without prefix sums. So again, prefix sums are basically allows us to compute range sum queries in constant time. And then a lot of times when you see constant time, you can treat this as just like this is one operation. Okay. So if we go back to our sort of general estimate of time complexity, let's look at how this would change, right? So 10 to the power 5 queries we still need, but inside this, right, prefix sums will be able to take care of this sum query in constant time. So instead of 10 to the 5 operations, we'll just have one operation. And this will be 10 to the power of, this should be 10 to the power 5, right? And this is less than 10 to the power 8. So we can see that with prefix sums, we'll be able to get this program running in time. In the next video, we'll just do a review about how prefix sums works.